Rearranging radical functions. Depending on how tall you are, the horizon will appear at different distances. So the horizon being that because the Earth is curved, you can only see as far as that curve will allow you, and then things sink below the horizon. So if you're a little bit taller, so for example, if I drew a blue guy over here that's a little bit taller than this red guy, he would be able to see slightly further. I'm not drawing a straight line here. I have to erase this. He would be able to see ever so slightly further than the slightly shorter person. And if you can get up to really high distances, you can start to see a lot further. So for example, this plane flying at 35,000 feet can see to this distance here. And the satellite flying at, I don't know, I don't actually know how high satellites fly, but maybe there's thousands of feet in the air, they can see further. And there's actually a nice formula that we can use to calculate, given a height above sea level in feet, the horizon distance in miles can be estimated with this formula. D is equal to the square root of 3h over 2. The example we're going to show you now is how to rearrange this formula for h. So really this is like solving a radical equation, only we're going to do it without getting some value at the end. It's going to be solving it for h, but we're still going to have this other variable d in the equation. So to solve this equation, what would we do? So we have d equals the square root of 3h over 2. And to solve it, we're going to square each side of the equation so that h is free and not stuck underneath that radical anymore. So on the right-hand side, I have d squared. On the left-hand side, my radical goes away, and I have 3h over 2. Well, what's the next thing I need to do to get h all by itself? I'll start by multiplying each side by 2. So then I have 2d squared is equal to 3h. And finally, I will divide each side by 3. And that leaves me with h all alone on the right-hand side and 2d squared over 3 on the left-hand side. So this is my final equation for h. I've rearranged the formula. And now, if I need to be able to see a certain distance to the horizon, like if you need to put a satellite somewhere so that it can see a certain location on the globe, you can calculate what height you'll need to put the satellite at for that purpose. Another interesting example of a radical equation comes from the medical world. So sometimes doctors calculate a patient's body surface area, BSA, when deciding on the dosage of a drug. And the BSA can be calculated, it's an estimate, but it can be calculated based on their height in centimeters and their weight in pounds. And their BSA is in square meters. The result is in square meters. But this formula has been developed so that you get a good estimate of the BSA based on those two variables, height and weight, in those particular units. And in this example, we're going to rearrange the formula for W. So similar to the previous example, what we have to do when we have that radical is square each side to free the variable that we're interested in, to get it out from underneath that radical. So now I have BSA squared is equal to WH over 3600. And now I will multiply each side by 3600. And I get 3600 BSA squared is equal to WH. And now because we're rearranging for W, we're going to divide H away. And my final answer would be W is equal to 3600 BSA squared. I'm going to put that all in brackets just so that you can tell that BSA is one unit together, divided by H.